Welcome to today's webinar on flow rates. Let's start by understanding why flow rates are important. So first, if you design a flow rate that is lower than what the building will experience, you're going to have problems because your pipes will be too small. This means that the water might not even make it out of the tap because of really high velocities and really high pressure drops. But if you design for a flow rate that is too high, you're going to oversize all of your pipes, valves, and equipment. So not only is this an unsustainable design, it's going to lead to an unhygienic system, and there will be excessive cost to install and operate that system. So as an engineer, if your design causes either of those problems, it's going to be non-compliant, which puts a lot of risk on you and your company's reputation. And it's going to cost a lot of money to fix, and nobody wants to pay that. But don't worry, because these problems only occur for engineers who don't do their calculations. There's nothing to worry about if you do your calculations, so you're in the right place to learn about this today so that it won't happen on any of your projects. Okay, so let's take an overview of what is involved in these flow rate calculations. There are two different types of flow rates, and it's very important to know the difference. Firstly, we're looking at diversified flow rates, which means the flow rate which is calculated will diversify based on the number of fixtures connected and the probability that they will be running simultaneously. If there is just one fixture, like we have here in this example, the probability is that fixture will run. So the pipe is sized based on the flow rate. But it isn't always a direct sum. So as you add more fixtures, like we have here, the flow rate will increase, but it's not linear. A probability is applied. So we have 3 fixtures, all at 0.1 litres per second, but combined, the pipe is only sized for 0.2 litres per second. And this is called a peak demand. It's essentially saying out of these 3 fixtures, the probability is that only 2 will run at once, so we are going to size just for that 2 to run at once. The second type of flow rate is called a continuous flow rate, and this gets added directly onto the system. So there is no probability and it doesn't get diversified. So for example, we have 2 continuous flow rates here, both at 0.5 litres per second. Combined, they equal 1 litre per second. So again, no diversity or probability here. And then when a pipe supplies both continuous flow rates and diversified flow rates, you calculate them both separately and then add them together. So looking at this pipe, for example, where we have 1.1 litres per second, we have the 1 litre per second for the continuous flow rates and the 0.1 for the diversified, although there is no diversity in this case yet. But then if we look at the pipe supplying the whole building, once again, we have the 1 litre per second supplying the continuous flow rates, and then we have the 0.2 litres per second supplying the diversified flow rates. So here we've got the 0.2 for the diversified and the 1 for the continuous. Add those together and that's where we get the 1.2. So in summary, a diversified flow rate is where you look at the loading units, which are units assigned to each fixture, and then convert those units to a flow rate. And it's important to understand it's not linear. So if you look at the blue column, for example, for 10 loading units, the flow rate is 0.54. Then for 50 loading units, we don't times the flow rate by 5. It's a completely new diversity and probability, so it is now only 1.07. And then once again, as we go from 50 to 100, we don't double the flow rate, we look it up again, and it's increased from 1.07 to 1.35. So just as an example, if you've got one fixture, probability it's going to run is 100%. If you've got 10 fixtures, maybe there's a 30% probability. 100 fixtures or 1,000 fixtures, that percentage of fixtures running at the same time will decrease. And then we have continuous flow rates, a lot more simple. There's no diversity, no probability. Whatever the number is, it gets added onto the flow rate. All right, well, let's go through some real-life design scenarios now so we can make these flow rate calculations feel like second nature to you. In this first example, we're just going to go over some basic scenarios to help you grasp the fundamentals. So here we've got a very simple layout and we've got one fixture, a WC. So these fixtures do have their own loading units. So here a WC has 2 loading units, and this will convert to a flow rate. So as we click results, we can see here that those 2 loading units convert to 0.12 liters per second. Okay, so now I'm going to add one more WC, and while I do that, have a think what you expect to happen to the loading units and also to the peak flow rate. Okay, so here we can see that the loading units are linear, they've gone up. So 2 plus 2 is 4. However, it's the conversion to the peak flow rate that isn't linear, and we can see that that has only gone up 33%. Okay, so in this next example, I am going to add one more WC, and once again, just have a think what you expect to happen. So loading units have gone up linearly to 6 now, but the increase in the peak flow rate has only gone up by 25%. So hopefully you can see now that as you add more fixtures, the flow rate will always increase, but the amount it increases by will reduce. Now we're going to look at a similar scenario, and instead of the fixtures, we're going to replace them with continuous flows. So I'll just delete these 2 to begin with, even this one. And using the node, we can drop this on the design. So here we've got 1 liter per second at this node. I would leave it like that. So just have a think as I click results, what do you think the flow rate through this pipe will be? It is 1 liter per second. So there is no loading units here. Again, no probability, no diversity. 1 liter per second continuous flow is 1 liter per second. So I'm going to add another node now, which will be worth 2 liters per second. So altogether, there will be 3 liters of continuous flow. What do you think the flow rate going through the pipe will be? So the answer is 3 liters per second and then 1 liter per second, because they're just being added together. It's as simple as that. And in this last example, let's combine the 2 types of flow rates. So I will copy both of them and combine them into one layout. So here we can see that the peak flow rate is a combination of the 2. So they're treated separately. So the 3 liters per second for continuous flow rates is also here. But then the 0.2 liters per second, the diversified flow rates, is just added on top of it. So coming in, we've got the 3.2 and still based on 6 loading units, but we have the 3 liters per second of continuous flow. So I hope that makes sense. Just to recap, continuous flow rates, simple additions to each other, and that will then get added on to the next calculation, which is the diversified flow rates, which will increase in flow rate the more fixtures you have, but the amount it increases by will reduce every time. Let's look at a little bit more complicated project here where we have hot and cold water pipes supplying the same fixtures. So the cold water comes in from the right to the left here, as we can see with the arrows. It supplies the basins, but it also supplies the hot water plant, which will supply the basins with the hot water. So if we look at the results on these pipes, starting on the right here, there is 4 loading units, which is correct because each basin is 1 loading unit each. Then you might notice after every branch takeoff to the basin, the loading units and the flow rate are not decreasing. The reason for this is because if this cold water pipe wasn't supplying the hot water plant, then yes, the maximum flow rate coming through this section of pipe is 1 loading unit. However, in the scenario that nobody's using the cold water, but everyone is washing their hands with hot water at the same time, if this pipe was only sized for 1 loading unit, it's going to be undersized, because for the 4 loading units of the hot water system, that needs to come all the way through this pipe and then around. So just important to understand that you're not just sizing the pipes based on what is connected when it's a cold water system. You do have to look ahead at the system as well and just check, is there a potential that more flow rate would come through this pipe? And in this situation, there is. Okay, and then the next thing on a situation like this is we have chosen in the settings on this project that we don't want a cold water pipe that supplies both the hot and the cold water to combine the hot and the cold loading units together. So what I mean by that is essentially we're saying that if somebody's using this fixture, they can't use the hot and the cold at the same time. And because that's not possible, the loading units are 4. So this would be like if the tap only has one outlet, for example, you can't turn the hot on and the cold at the same time. But it is possible with some fixtures. So you can potentially might have 2 taps, one for the hot, one for the cold, which in that case you can turn them both on. But I'm just saying this because it is important to understand what your project fixtures will be able to do. Because for example, you can change to combine those units together. And it's really important to do that because as we can see now, this pipe has doubled because it's supplying 4 for the cold and 4 for the hot, and then 7, 6, 5, and 4. So it's important because obviously as the loading units increase, the flow rate will increase as well. And as we mentioned at the beginning of the presentation, if you get this wrong, you're getting all the sizing wrong from the components to also like the velocity and the pressure calculations as well. So just something to be aware of. Is a cold water pipe supplying both hot and cold at the same time? And even if it isn't, you still need to make sure that you don't undersize the pipe that supplies the hot water plant. Okay, to summarize everything and to act as a checklist for your next calculation, the steps that you need to follow are to choose your peak flow rate calculation method. This will differ based on the location you're in and the standard that you're using. You'll also need to find out any continuous flow rates on the project, which you can get from members of the project team. And then on a pipe, you need to calculate the diversified flow rate and then add the continuous flow rate. So just remember they are separate and then get added together. And then you'll need to follow the same process on every pipe segment through the building, both on the hot, the cold, and anything else. And then once you have your total flow rate, you can use that number to size all of your system correctly. That is everything for today. I hope this helps you with your future designs. If you've got any questions about the calculations or you'd like to know more about H2X's design software, you can reach me directly at jonathan@h2xengineering.com, or you can check out our website, h2xengineering.com, where there are lots of other technical resources similar to this one.